Yeah, hello everybody. So another try. In between, I will save just once the video that it hopefully doesn't crash if I cut it into pieces. Okay, yeah, what have we done yesterday? More or less, I would say we calculated linear regression more or less by hand, not with a pen and a paper, but that we really go through all the calculations in order to get our estimators, which we need. So this beta value we need, and then where do we have it? Here, all these matrices multiplied with each other. Maybe I can copy this again, or I have it already, I think. Yeah. So this one, so we have to identify what is our matrix X, we have to invert it, and then afterwards multiply this with the transponed and with the output vector Y, and with this we obtained then our result for our three values. Beta, that we then could say that we had in general our ansatz Y is beta 0 plus beta 1 x1 plus beta 2 x2. Well, and yeah, in the next step, then we can, so to speak, calculate the values which we would obtain theoretically if we apply our three estimated values beta. And this we will then do. So here are our beta values, and y hat in the simple linear case, regression case, then it would be that these are the data points which are lying on the regression line itself. Here we have a three-dimensional problem, so still we can imagine it in a three-dimensional space. So this will be then the points lying on a plane. And if we go further, then of course it's hard to imagine four-dimensional or six-dimensional space. But this we will then calculate. So the value which corresponds to the x1 and x2 values 1 and 1.2 is then beta 0. This we have to fix because afterwards we want to copy down this formula. So F4, then you see here that in front of L and 5 you have this dollar sign. This means if you copy this formula that it still will be related to this number beta, to this cell L5. So plus beta 1, oops, sorry, no, again, no, plus beta 1. This is the estimator for x1, so times 1. No, sorry. So again, beta 1, also fixed, times. So you see it here, up there, oops, that this is then the formula that you know what I'm doing. And times then 1.2. and then not 1.2, we are at 1.1. This is beta 1, x1, and now plus beta 2 fixed times x2. So our corresponded estimated value from our regression with the input parameters, the input variables for x11 and 1.2 would be then roughly 1.75. Our real data point, we obtained a revenue of 2. And so then we have this discrepancy between the empirical data point 2 and our, so to speak, theoretical data point 1.57. And this, you remember, in the simple linear regression is then just the distance between the point itself and the corresponding point on the regression line. Okay, and this then we copy down here, and then we know all the theoretical points corresponding to our data points for x1, x2. So if we click in here, then you see that this is highlighted, that you have here beta 0 plus 0.98 times 7 plus 0.151 times 7. Okay, so later on, right now, then we want also to, what is our task? Calculate the coefficient of determination. And for this coefficient of determination, we know in general that it is just, where do we have it? Oops, here. The explained variance over the total variance. And this I will again also show you in the two-dimensional case. This was that we have our data points somewhere lying there. This would be maybe our regression line, so y and x. And then we have in general average of all our y data points, y bar. And remember, we are calculating at first always these averages because we want to have one representative for our distribution. And what we are doing more or less with a regression line, we shift, so to speak, this horizontal line a little bit so that in general all our data points are more in the neighborhood of this regression line. And then we say, well, this movement more or less then explains something of the variance, because with respect to the average we have this large variance, and now we have here a little bit smaller variance. And this, of course, then we have to do with all data points. So this is the explained variance, and this is the total variance. So what we now need is the difference of our theoretical values, y, which we just calculated, with respect to the mean, and the total variance, just our data points with respect to the mean. So then we need the mean, and this we have done quite many times in this lecture. There you have also the formula, and in general it is just summing up all my data points and dividing it by the number, the amount of my sample. So divided by 7, and if you choose the function, then of course it is directly done, or you can do it also by summing up this and dividing this by the number 7, then of course we have the same number. So then one question: if I am copying this formula to the right, so summing up all theoretical data points and calculating the average, which kind of number do I obtain? Yep. No, not already. Now we just want to calculate the average of our, so to speak, points lying on the regression line. Well, let's do it. And what happens? It's the same number then on the left. So this is the average of these points, and this is the average of these points. And is this very surprising? If I'm asking like this, then of course it is not surprising. Well, and if you remember when we introduced the regression, then we said that the average of our data points has to lie on the regression line. Remember in the simple case, we had that y bar is a plus b x bar. And this we showed in general for the simple regression, and this holds also in the multidimensional case. So this is then not surprising. The other way around, it is a possibility to check your calculation, because if this is not the case, then something has to be wrong in your formula. So, and now we calculate these variances. So what we need y minus y bar. This is then open y minus y bar squared, and since I want to copy it down, I forgot to fix it. Then we can go down. So y bar, this we just put also here that we know it. So all the data we need. So this is then the total variance, and this is the explained variance. Let's format this. So, yeah, you still need this. Okay, and since this is almost the same formula, I just copy it to the right, and now we need not the column F, but we need the column G, because it is y hat minus y bar. So interchanging this with G, we obtain all the single squared distances, and the total variance is then the sum of all these numbers. So this is the total variance, and this is the explained. Okay, so this one, and this one. Let's take this data also. So, and now we have everything together in order to calculate our coefficient of determination. Then r squared is what? What do I have to do now? An idea? Just look at this formula here. We have the explained variance over the total variance. Yep. Yes, but this I've already done, or? Yeah? Yeah. Yeah, definitely. So we have to divide 62 by this 63 point. Oh, sorry. Okay, then I have to, this I can change to, that we then increase here the size, maybe 130. Better? Okay, sorry. Okay, I think this one I don't need. So, and then I can move this a little bit to the right. So I still want that you see all the menus. So if you later on, and hopefully today it will record, that you want to know, well, what has he done, then a video is quite good. And this I also recommend if you try to start to use Excel a little bit more. There are really many very good tutorials within in the internet, and just try it. Okay, so then we can calculate r squared by 62.5 divided by 63.7, and this is 0.98. So here we have our r squared, and this is then our, what do we have? 62.52 over 63.71. Yeah, and then we of course also want then do these hypothesis testing. So right now we only have done the descriptive part of our regression. We obtained these beta values, so we can then say if what was the first was the number of inhabitants. If we are going to another city with 10,000 more inhabitants, then we could assume that due to our descriptive regression, the revenue raises by 0.4, not 0.4, beta 1, almost that we almost have a one-to-one increase since beta 1 is 0.98. So moving to a city with 10,000 more inhabitants would then mean my revenue is increasing by 10,000 euros, but only from a descriptive interpretation, or that if I increase the size of my store by 10 square meters, then this would mean that my revenue increases by €1, so to speak, or €1.50, since I have 0.15. And then I'm maybe quite happy because I've found then a coefficient of determination of 0.98. And what does this mean? This means that my data points are, my empirical data points are really in the neighborhood of my now not regression line, but my regression plane, so to speak. So this maybe is then what makes me quite happy, because I look more or less on the data and I see, well, I fit the data very well with my regression. But still, and this is really important, I'm only in the descriptive part. I still cannot make a statement that, well, from a statistical point of view, this fit is a very good fit, qualitatively spoken. So I still cannot make the statement with 99% probability this is good, or this is the right model which I have calculated. And for this, then in general, I need this standard error of y. And why do I need this standard error of y? This I introduced also. This was here. Because what do I need? I have now estimated my beta parameters, and it is only an estimation. And since it is an estimation, then I roughly can imagine this means, take a beta 1, this was 0.98. So in general, then I would say I have some fluctuation, some interval in which this is this parameter is situated. So we always then think 0.98 plus minus 0.1 or something like this. And how large is this fluctuation? And for this fluctuation, we then need the general variance of the output data, my y data, which I want to explain, because these fluctuations one can show is directly related to the fluctuation of beta, and this is via this dependence here, that the fluctuation of my beta values are the standard error of y, of my output data, my revenue data in my example, times the diagonal elements of these famous matrix we have already calculated, inverse of xt times x. And having the assumptions, all is independent in your term papers. you have to deal with the practical issues that in most cases they are not all independent, and that we assume that the errors are normally distributed as the fifth assumption. And with this together, one can show that then also the beta estimators are standard distributed with then the variance where we have to calculate the standard deviation of y times these diagonal elements. Okay, and what was y? There also we have, so to speak, to rebalance it. At first, of course, the variance is of y is just the values of y with respect now to our regression, and then divided by n minus the number of our estimators. Okay, then let's go back to our example that we now want to calculate as standard error of y, and this is then in our case 1 over n, there we have 7, minus k, number of our fitting parameters, 2. So this is the number of our explanators, so of our two independent variables, x1 and x2, plus 1. And now the sum, and this is now important, not with respect to the average, but what we still haven't explained by our regression. So this is then yi minus y hat I. So in the two-dimensional case, we are now interested here always in these distances here with respect to the regression line, in our case a regression plane. So squared. Okay, so in this case we need also this column here. This is of course again almost the same formula as we have it here. So I copy it. Now it is E minus F. So this I have to replace by F5 and then moving this down. Okay, let's take this sum away here. And how much, what level of number do you expect if I'm copying now the summation to this part? Is it about 10, 15, 16, 50? What would you expect if I press enter in a second? Yeah, lower than 1. Almost. I would expect it is a little bit larger than 1. And why do I expect this? Well, I think you have just looked at the numbers and saw, well, okay, it's 0.2, it's 0.5, it's 0.08. But why do I expect roughly 1.2? Without summing up in my head the numbers. An idea? What do I'm calculating now? I'm calculating now the unexplained variance. So, and if I have already the total variance, and the explained variance, then this number should hopefully be just the residual between these two numbers. So let's see if I'm right. 0.17. This is a little bit. Oh, I copied the wrong formula. So this is also, I think, this is a nice mistake I made now. Because what did I do? I did take the formula that I take the average, but I want the sum. So hopefully if I multiply this now with 7, then hopefully I obtain these 1.2. So roughly it is. And of course, this we can check that this has to be the same number, total variance minus explained variance. And of course, this is the same. Or what I also can do, this is the right formula, only the sum. And if I copy this here, then of course I get also the same. So, and then I obtain SEY squared. So the variance with respect to my regression of the revenue data points is then this number divided by n. This was 7 minus 2 unexplained, 2 independent variables, x1 and x2, plus 1 brackets closed. There is something wrong. This I don't need. And so I obtain 0.21. And what do we in the end need? In the end, we need the standard deviation, and the standard deviation is just the square root of the variance. So then we have SIY is then the square root of this number is 0.54. So this is then, what do we have, 1.19, or I can also write it down since I have these two numbers here. This is then 63.7 minus 62.52 over 7 minus 3 is 4, and then we have this here. There. Sorry, and here I did a mistake. This is not already the standard error. This is the variance and the unbiased variance, and then we obtain the standard error. So this is SEY squared. SEY is square root of 0.298, and there we have this number here. So So then, since it worked until now, I just save it once.